inertia vector in the center of mass, please? You need to do that anyway for Newtonian mechanics, right? And you only differentiate once. So this is negative x dot L over 2 cosine theta theta dot minus L over 2 sine theta theta dot shade. And you need to do it again for Newtonian mechanics, right? Luckily here we differentiate only once. So I can get now the kinetic energy, the first term, the translational kinetic energy, 1/2 mv squared, but I need also the second term. The second term here is easy. So T translation is what? Is 1/2 mRc dot squared, which is 1/2 m. Please do the rc dot squared carefully because it's two components. Each component is squared separately. So this guy is x dot squared plus L cosine theta x dot theta dot plus L squared over 4 theta dot squared. Okay? I need the second term, the rotational kinetic energy, which needs I and omega. Here is pretty simple. You can actually get it because it's single rotation, right? It's a single rotation. What's the angular velocity? What's the angular velocity?
Theta dot.
Theta dot. Because it's a single one. Next time we'll do a more detailed one with multiple rotations to do it in detail, the 1/2 omega transpose I omega. Right now, I'm just gonna add 1/2 I omega squared. My omega is theta dot squared. And the moment of inertia on the center of mass is simply, ml squared over 12, right? So this is your total kinetic energy now. So 1/2 I omega squared. Let's write down your kinetic energy. So it's 1/2 m x dot squared plus ml over 2 cosine theta x dot theta dot plus, you're going to always have theta dot contribution from here and from there. So add them together. What's that? This is 1/8 and 1/24. So 4/24, so 1/6. ml squared theta dot squared over 6. Any questions so far, please? All what I did is adding one extra term, this green term, 1/2 I omega squared. This is a single rotation. If it's a general rotation with 3 components in omega, here is the term, 1/2 omega transpose I omega. We will do it next time. This is your kinetic. What about your potential, please? It's what? It's mg times what?
L by 2 cos.
Yeah, the center of mass, it's L over 2 cosine theta, and it's positive because it's up the datum. So I can construct my Lagrangian, magic Lagrangian, T minus V, 1/2 mx dot squared, ml over 2 cosine, ml squared over 6 theta dot squared, minus mg L over 2 cosine theta, okay?
Professor,
Yes.
shouldn't that be ml squared theta dot squared over 24? Instead of
But we have 4. This is what? 1/2, 1/4, so this is 1/8. Plus 1/2, 1/12, this is 1/24.
Yeah,
So this is 4/24,
yeah, I didn't see that.
right? So it's 1/6. Okay, you got your Lagrangian. Let's do it. Partial L partial x is what? 0, right? There's no x in this equation. And this is understandable. X is an ignorable coordinate. X does not affect your dynamics. Why? Because simply if I start this motion, here it's as if here, it's as if there, x doesn't affect my dynamics, right? So partial L partial x is 0 and no QNCX and no constraint, right, in the x. So this immediately tells you what?
Cyclic coordinates.
Exactly, that x is an ignorable coordinate or cyclic coordinate. what is the implication?
Translation momentum is conserved.
Yeah, the corresponding momentum is conserved. How do you get the corresponding momentum? Don't bother yourself. Here is how you get it within the framework of Lagrangian mechanics. Partial L, partial x dot is constant. Differentiate with respect to x dot, please. You get here m x dot and L over 2 cosine theta, right? No? I guess, yeah, I guess this was minus. Will not affect much, but that's okay. This should be minus, because this is minus. When you square it, you get minus here. So this means this guy is minus. This guy is minus. And finally, we get minus. So partial L, partial x dot, this is constant. I'm going to call it px, the linear momentum in the x direction. And this is conserved. And I guess you know very well now why this is conserved, right? Because look at the problem from the beginning. No forces whatsoever in the x direction applying at any point, right? Because this is frictionless. There is no friction on the floor. The normal force is vertical. The gravity is downward. There is no any force in the x direction, so the momentum in the x direction is conserved. You can get that from the Newtonian mechanics, but here is a constructive way to get it. Yes?
Shouldn't that be L by 2 cos theta theta dot? Theta dot.
Theta dot, yes. We have theta dot here. Thank you. So I got the conservation of linear momentum. I got a very useful piece of information that I can use to get x dot. How to get a value for px? From your initial conditions. So if we start at rest, what's this px? 0. Why? Because it's x dot naught, theta dot naught, both are zeros. So this guy is 0. So you get immediately your x dot equals L over 2 cosine theta theta dot. I got x dot in terms of theta dot, and my problem didn't have any x. So no x from the beginning, and now x dot I can remove it, replace it in terms of theta dot. So I can live only with it. I reduced my system. Okay? How to do it? How to reduce your system? How to reduce the system? Lagrangian. Please don't get this guy, because it's very tempting, right? To get this guy and put it here. Okay? In this particular problem, it may work. Why? Because here is the Ruthian. The Ruthian in general is what? Is your Lagrangian minus. Minus what?
Px
Px dot. Very good. Luckily in this example, because the initial momentum is 0, the Ruthian is the Lagrangian. So it will work in this example. Other than that, it will not work. So let's substitute in every term in our Lagrangian by the x dot. So I have 1/2 m x dot squared. So this is L squared for cosine squared theta dot squared minus I have m L squared over 4 cosine squared theta dot squared, so I have the same term, plus ml squared theta dot squared over 6 and mg L over 2 cosine theta. So these two terms, I have 1/2 minus the other, so I got minus 1/2. So this is minus ml squared over 8. Yeah, right? Yeah. Minus cosine squared theta, theta dot squared. So your Ruthian is ml squared over, how to do this? Maybe 24. Theta dot squared. So this is 4 minus 3 cosine squared theta minus mgl over 2 cosine theta This is actually 1 plus 3 sine squared theta. You can write it either way, whatever you like, just to match the solution. So I have my Ruthian that's function of theta only. I'm going to apply the Lagrange's equation. d by dt partial r partial theta dot minus partial r partial theta equals 0. So what do we get here? We get ml squared over 12 theta dot and this thing plus another term. So ml squared. No, that's right. This guy we need to differentiate with respect to theta. So I have ml squared 24 theta dot squared. You have 3 and 2, 6. So this is 4. What else I have here? Negative, and I have, this is sine squared. No, sine squared, so it's sine theta cosine theta. Now from there we have plus mgl over 2 sine. Do it whatever you like. Here is the final answer. Theta double dot equals, right? So we did it. Let me copy the final answer. Do you have any question, please? Any question? 6 minus 3, 3. Okay. Any question?
So why that substitution fails? Why can't we do that? We have got one variable, we can put it over there. You say it will fail, not a good method. Why it fails? Because of this angular momentum. This is momentum, sir. But
This is a way. This
is a way against that way. So why
Yes.
this is a way and why that is not the way?
because it doesn't preserve your dynamics. Your original dynamics inherently has 2 degrees of freedom. And if you think of this as a constraint, this is a conservation of momentum. If you think of this as a constraint, okay, it's a non-holonomic constraint. It's not a holonomic constraint. A non-holonomic constraint, you can completely ignore a coordinate. Okay, you cannot completely get rid of one coordinate. So the scientists devised a means to allow you to do that. So the means dictates that you have to subtract these terms. It's not from the beginning, no, why shouldn't they do it? Because your dynamics is intrinsically on 2 degrees of freedom, it's not on 1 degree of freedom. Okay? And your constraint, if you view it as a constraint, it's a non-holonomic constraint. You cannot completely get rid of the degree of freedom.
So in this way, the dynamics is preserved even with a single degree of freedom.
Yeah, because you start with the initial 0 momentum. The question now is, remember the requirement was to get theta dot as a function of theta. Theta dot as a function of theta. Your theta double dot is not function of position only. If my theta double dot is function of position only, I can play with different games, right? I can, one of two things. I can define this as negative dv effective by d theta and plot the v effective and play with the equilibrium and stability. Or remember v dv by dx, or omega d omega by d theta, right? Do separation of variables and integrate. So you can get omega as a function of theta. Neither works. Why? Because the right hand side has theta dot in it. It's function only of position, theta I can do great stuff. It's function of theta dot as well. This is highly nonlinear differential equation. You cannot do anything analytical about it. Go and numerically integrate it using MATLAB or something. So the question now is, yeah, this was required, the equation of motion. We're done. But there is another requirement. They need theta dot as a function of theta. How can we get it? Theta dot is velocity, right? You need to relate velocity to position. What equation in dynamics ever can do that? Relate velocity to position. Just think deeply for a couple of seconds. Velocity to position. Why are you laughing? What equation? What relation in dynamics that can ever relate velocity to position?
Newton.
Newton gives you acceleration, right? It's very similar to this equation. A equals or x double dot equals. It's conservation of energy. Kinetic plus potential is constant. Why? Because kinetic has the velocity in it, potential has the position in it. So immediately you relate velocity to position by conservation of energy if energy is conserved. Luckily, energy is conserved in this example. Why? Because you don't have any time dependence, right? And we don't have non-conservative loads. So energy is conserved. Your H is conserved. Okay? How to get your H? It's kinetic plus potential. Why? Because here is my kinetic. Every term is quadratic. Quadratic, quadratic, quadratic. If your T is quadratic, simply H is T plus V, which is 99% of our problems will be the case. Your H is T plus V. If you like to construct it from the Lagrangian, that's fine. Get the quadratic term here. Here is the quadratic term, right? And here is the term that has no dependence. R2 and R0. Subtract them to get your H. So your H, where should I use? Maybe here. Your H, it's either T plus V from the very beginning or R2 minus R0. Let's do it R2 minus R0. What is R2? Here is R. R2 is the term of quadratic in velocity, theta dot square, this whole term. So this is ml squared theta dot square times the bracket. The bracket is 1, 3 sine square theta. Minus R0. What is R0? The term that is free from velocity.
MGL.
It is the term that is free from velocity. It has a minus in it. So this indeed is a plus. mgl over 2 cosine theta. This is constant. So it's equal, its value at the beginning. So at the beginning we have some theta naught initial disturbance from rest. So this guy vanishes and I have this guy only. So equals to mgl over 2 cosine theta naught. So you can immediately get theta dot as a function of theta, right? So theta dot is the square root of something. What is this thing? It's